Hi, welcome to the inaugural talk at the Iowa State Geometric Analysis Seminar. Today's speaker is Pablo Raul Stinga, who's a professor here at Iowa State. Before coming here, he was an R.H. Bing Fellow at the University of Texas, Austin. Today, he will be discussing regularity for C1 alpha interface transmission problems.
Thank you very much, Gabe. It's a great pleasure to be the first speaker in this new seminars we're launching here. If you have questions, probably you can just message me on the chat. So I'm going to talk about joint work with Luis Caffarelli and María Soria-Carro. So María, she's a PhD student at UT Austin, and Caffarelli and myself are her advisors. This is a paper that appeared in ARMA in 2021. So what is a transmission problem? So transmission problems, as it says here, concern situations where the medium changes behavior across a given surface or interface. So let's just talk right away about examples, right? One of the oldest examples, perhaps, is the Fresnel equations. They talk about reflection and transmission of light when incident on an interface between two different optical media. No? So here's a picture of the duck, right? The light on the air changes direction when it goes through the surface of water. So you see that the duck is like split into two, and this is the diffraction. So there is an equation, the wave equation, right, for the light in the air, and there is a wave equation for the light in the water. And then when the light passes from air to water, something is happening at the interface. There is a transmission that is happening that makes the solution discontinuous, as you can see here. Other examples are from elasticity, where you have two materials that are glued together, and then one material pulls the other. So perhaps mathematically, the first one to put this problem was Mauro Piccone in 1954. He proved uniqueness. Then Jacques-Louis Lyons proved existence in the Sobolev space. And then also Stampacchia did contributions, and then Campanato generalized to other equations, and Schechter to other non-divergent form equations with smooth coefficients. Then we have another example of composite materials, which is, a bunch of materials put all together, right, glued together. For example, there's the work by Lee and Nirenberg, and these equations can be thought as equations. On each material, there is an equation, and the coefficients in the equations, when you pass from one material to another, are discontinuous. Diffraction problems by Ladicenska and Uraltseva, again related to optical media in the 50s and the 60s. And then there is local non-local transmission problems. For example, this work by Krivensov on atmospheric dynamics. So, for example, there is an equation that is non-local on the surface of the sea, the quasi-geostrophic equation, and say you have another equation on the land, say the heat equation, which is a local equation. When you pass from the land to the sea, right, the temperature changes, and the interface will be the beach. There will be a transmission surface. And many more examples. Now you can think about running into the beach. When you run into the beach, right, you have an equation for yourself, right? And as soon as you hit the water, you start to sink, you start to slow down, right? So there is another equation, and the transition was the beach. All right. So what is the transmission problem that we studied? It's a transmission problem for harmonic functions. So you have a smooth bounded domain omega in Rn, and you have a compactly contained subdomain omega 1 in omega, and whatever is left between omega and omega 1, that's omega 2. And then the interface is the boundary of omega 1. And we're going to call nu the normal on gamma interior to omega 1. So here is the picture. Is domain omega. You have an interior domain omega 1. The normal is pointing inside, and then whatever is left is omega 2, and you have the interface gamma. Now, if you have a function defined the whole omega, we're going to use some notation here. U1 is the function u restricted to omega 1, and u2 is a function restricted to omega 2. So what is the transmission problem? We want to find a continuous function u defining omega that is, say, 0 on the boundary of omega, such that the u1 is harmonic in omega 1 and the u2 is harmonic in omega 2. So harmonic here, harmonic in omega 2, and then the normal derivative of u1 with respect to nu, so the derivative in this direction of u1 minus the derivative in this direction of u2 is prescribed. Okay? So what are the transmission conditions here? There are two transmission conditions. First, u is continuous. So it means that u1 and u2 agree on gamma. No? And then the derivative, the normal derivative of u1 is the normal derivative of u2 from the other side plus this g. Before continuing, let's put an example in dimension 1 so we understand what is happening here. So say omega is the interval minus 2, 2. And omega 1 is the interval minus 1, 1. So then whatever is left is the omega 2. So the interval minus 2, minus 1, 1, 2. And then the boundary of omega 1 is the interface. So the points minus 1 and 1. So that's the gap. So again, the problem is a harmonic function except at the boundary. So except at minus 1 and 1. And then at minus 1, the derivative of u1 minus the derivative of u2 is some alpha. And at 1, the other point, the difference is some beta. Okay? So what is the picture? U second equals to 0 is a bunch of lines, right, that are 0 on the boundary. So are 0 on the boundary and there are lines. No? So let's see. So suppose this beta is 1, right? So here, the u prime of 1 minus u prime at 1 is beta. So the u prime at 1 arrives with this slope, right? It has to be beta plus the slope of this one, right? So there is this angle that is created because you have this beta. If alpha here is 0, right? If alpha is 0, it says that the derivative from one side is the same as the derivative from the other side. So there is no angle, okay? So say now we keep the angle beta equals 1 in the point 1, and let's increase the value of alpha. If alpha is 0, just a straight line. If alpha is 1, then we have the same angle as in here. And if alpha increases, alpha is 2, you have a more acute angle, okay? So this is a very simple example in dimension 1, but tells us a lot. First of all, it says that for the transmission condition to be meaningful, right, this alpha and beta have to be non-zero. Because if alpha is 0, then the function will be differentiable across. So there will be no angle. It will be just a harmonic function, right, across. So we're going to assume that alpha and beta are not 0, right? So you have an angle. And also you see that the solution here, that each piece is a harmonic function, no? They are smooth functions. There are always corners. So the global regularity that you expect here is U to be Lipschitz, no? And so that's also another thing that you expect. And the other thing that you finally expect is that this is a harmonic function, right, that arrives there, and this is another harmonic function that arrives there. So the hope is that the solution will be smooth on this side all the way up to the interface, and smooth on the other side all the way up to the interface. Not globally smooth, but smooth from one side and from the other side. All right. So again, here is the problem, right? Harmonic on omega 1 and omega 2. They coincide on the interface, and the difference of the normal derivatives is g. And we're going to assume minimal regularity. That is the interface gamma, which is the boundary of the interior subdomain, is a C1 alpha manifold. So locally, it can be represented as the graph of a C1 alpha function. And G, this data here, is going to be Helder continuous on gamma. So the theorem that we have with Luis and Maria says that there is a unique classical solution to the problem that is globally log Lipschitz. I'm going to write down in a second what does it mean. And also U1, right, in its domain omega 1 is C1 alpha up to the boundary. And U2 is C1 alpha up to the boundary, right? And with the estimates, C1 alpha norms of U1 and U2 controlled by the Helder norm of G, and a constant C here depends on N alpha and gamma. Okay? So this is the expected result, right? Because you have a harmonic function in the interior is smooth. Let's say the normal derivative, right? Think about the Neumann problem. The normal derivative being G says that the normal derivative is C alpha, right? So it means that the U should be C1 alpha, no? Up to the boundary. And that's what we prove, right? And also the regularity here of gamma, it has to be C1 alpha, right? Because if you expect U1 and U2 to be C1 alpha up to gamma, right? This is where these two functions coincide. This gamma should be, a level surface should be C1 alpha, okay? And this is minimal regularity assumption that we take. Here, by the way, I put that U is 0 on the boundary of omega, but that's not a restriction because you can put U equals phi on the boundary of omega, right? Because if you just take a phi on the boundary and do the harmonic extension inside, if you take this U1 and U2 and you add a harmonic function, nothing will change because there will be still harmonic, there will be still the same here, and the difference of the normal derivatives of a harmonic function, which is smooth, will be 0. So you get G plus 0. All right. So now what will be the notion of solution? That's the first thing we need to prove, that there is a solution. So what is the notion of solution? So as I said, the Laplacian is 0 outside gamma. And then on gamma, you have this difference of the normals being prescribed. So the notion of solution comes from computing the Laplacian of U in the sense of distributions. So you take a smooth function with compact support, and then the Laplacian of U in the sense of distributions acting on phi is the integral of U Laplacian of phi. But then omega is split into two domains, omega 1 and omega 2, and on omega 1, U is U1, and on omega 2, U is U2. Now, assuming that U is smooth, and U1 and U2 are smooth, right, everything's smooth, we pass the Laplacian of phi to U1. So when you pass the Laplacian here, by Green's identity, you get on the boundary U1 phi nu minus U1 nu phi. And here there is a minus in the Green's identity because on the boundary of omega 1, nu is the interior normal. Okay. So I do the same with the Laplacian of phi U2 here. I pass the Laplacian to U2, and then I get the same term now with a plus, because on gamma, right, the nu, the normal vector, is exterior to omega 2. Okay, so these are harmonic functions. So these two terms disappear. U1 and U2 are the same on gamma, because that's my condition. So these two terms disappear too, and you end up with minus plus minus U2. So you have the difference times phi on the surface, gamma. And this is my prescription, G. All right, I prescribe theta. So that's my definition of solution. A continuous function that is 0 on the boundary is a weak solution, let me say, to the transmission problem if the Laplacian of U is a singular measure concentrated on gamma on the interface with density G. Or in other words, the Laplacian of U is G on gamma in the sense of distribution, meaning exactly this identity that I wrote here. Okay. So that's my notion of solution. And now existence, uniqueness, and basic regularity can be proved. So even here, we can assume a little bit less about gamma. We can assume that the interface is Lipschitz and that G is bounded. Then the unique weak solution exists and can be written in this way. So the solution U is the integral of G on the surface against the Green's function for the Laplacian. Okay. And from here, from using this formula, one can check that U is bounded and U is log Lipschitz also with estimate depending on G. So log Lipschitz here means that this seminorm is finite. So in particular, if this seminorm is finite, then U is scalar continuous for any gamma of order gamma for any gamma less than 1. Okay? So existence of a weak solution, a solution in the set of distributions, follows from using the Green's formula, the Green's representation formula. Okay, so now that we have a weak solution, the solution is only Helder and log Lipschitz. Now I would like to prove that the solution is C1 alpha. No? This result here, that U is C1 alpha from each of the sides. Okay? So how to do that? All right, so let me review what will be a proof of Helder regularity of solutions of elliptic equations. Let me go back to just a single equation and see how you can do that. So there is a geometric way of proving elliptic regularity. This is a technique developed by Luis Caffarelli in this paper in Annals of Mathematics in '89. So what is the idea? I'm going to explain roughly what is the geometric way of proving regularity. So suppose you have a solution U to this linear equation that is elliptic, so the coefficients are uniformly elliptic, and it's in non-divergence form. So this is a matrix A multiplying the Hessian of U, and you take the trace, or summation here over repeated indices. So we have a solution to Aij dij of U equals F in the ball V1. And say the coefficients Aij are Helder continuous in V1, and the right-hand side is Helder continuous in V1. Then we would like to show that U is C2 alpha, right? Because here, if this is Helder and this is Helder, this should be Helder. The second derivative should be Helder. So U should be C2 alpha in the interior, because I'm not saying anything about U on the boundary. So a very naive computation will be in dimension 1. If you have the equation A of x U second equals F of x, then U second is F divided by A. So if this is Helder, U second is Helder, so U is C2 alpha. Okay? So this is the expected result, right? That U is C2 alpha if the coefficients on the right-hand side are Helder. Now the question is, how do you prove that? Well, you need to know what does it mean to be C2 alpha, right? Well, it means that the second derivatives are Helder continuous, right? But another way of looking at that more geometrically is, say you want to say that U is C2 alpha at the origin, at that point, the origin. Then what do you need to prove? You need to prove that U detaches from some quadratic polynomial in a C2 alpha way, right? So I need to find a quadratic polynomial P, which in the end will be the second order Taylor polynomial of U, right? I need to find a quadratic polynomial P such that U detaches from P in a C2 alpha fashion, right? So like x to the 2 plus alpha, okay? For all x less than 1/2. So this is the same as saying that U is C2 alpha, right? Okay, and this is called Campanato's characterization in this form, okay? So to prove that my solution is C2 alpha, I need to be able to find a second order polynomial, a quadratic polynomial, in such a way that I get this inequality, okay? All right, so how to do that? So say I want to prove that U is C2 alpha at the origin, then if we look at this equation at the origin at x equals 0, I can do a linear transformation to the matrix A, right? The matrix is elliptic, so diagonalizable. So I can do an orthogonal transformation here and assume that Aij at the origin will be the identity. And then F, well, F is a continuous function, right? So I can also assume that F at 0, say, is 0, all right? By subtracting a quadratic polynomial, essentially. So without loss of generality, we can assume that the coefficients at the origin are the identity matrix, and F of 0 is 0. Then what does this mean? That the coefficients are close to being the identity, and F is close to being 0 for x small, right? just by continuity, right? Because f is held there and the coefficients are held. So this should be close. Here I'm being very precise, but I just want to explain the idea. So what does it mean for u? If the coefficients are close to the identity, if the coefficients are close to the identity here, then this equation is close to the Laplacian, right? And if f is close to 0, then the right-hand side is close to 0. So the Laplacian of my solution is close to 0, in some sense, right? So in some sense, what we're saying is that u is almost harmonic, right? If my solution, if you have a solution to this equation, then very close to the origin, u looks like a harmonic function. So it should be smooth, right? So it should be smooth. So what is the key step? How do you really precise this, or more or less precise this? You say, I have my u in V1, and now say I look in V1 half. And I solve the harmonic function that has boundary values v on the boundary of V1 half, right? Then, because of this idea, if the coefficients are close to the identity and f is very small, because of this idea that u is almost harmonic, then this harmonic extension of u in the interior should be close to u, right? U should be close, v, this v should be close to u, say in V1 over 10, okay? To prove this, you use the maximum principle, okay? All right, so the key point is to approximate the solution by a very nice function, a harmonic function. Why can you do that? Because the coefficients are close to the identity and the f is close to 0. So you expect u to be almost harmonic. Okay, so its harmonic extension should be very close. And now with the v, you can construct this second-order Taylor polynomial that you need, because the quadratic part, p of v, so its second-order Taylor polynomial, is close to v, because, well, v is smooth, it's a harmonic function, right? So then you take the polynomial p, and you say, well, the difference between u and p, triangle inequality, is less than u minus v plus v minus p. But v was already close to u because of this result here. And now v is close to p by, this difference is like x to the 3, if you want, right? Because this is a C-infinity function, a smooth function, and p is its second-order polynomial, right? So then, in a very small ball, v lambda, you can see that the separation between u and p is of they separate at rate lambda to the 2 plus alpha, because this was small and this is small too, right? So then, at a scale lambda, u is close to a second-order polynomial, quadratic polynomial, right? And then what do you do? Well, you take that picture and you rescale to 1 and repeat. Scale and repeat. So you rescale everything to 1, and then you are back to the same situation. Then you find another polynomial that approximates at scale lambda. But that means that there are the sum of those polynomials, or a combination of those polynomials, will approximate very well u at scale lambda squared. And then you rescale again, and then you have an approximation at scale lambda cube, and so on. So at each scale, you find these polynomials that approximate u in a C to alpha fashion. And the idea is that then you pass to the limit, and you construct finally this polynomial p that makes this job. Okay, there's a geometric way of looking at doing elliptic regularity, right? Essentially, since the aij's here and the f are continuous functions, are C alpha functions, when you zoom in, right, the aij is becoming closer and closer and closer to the identity, and f is becoming closer and closer and closer to be a constant, say 0, right? So, and if you have some control on the way you're doing this rescaling, this is the C0 alpha properties of the coefficients and f, then you're able to transfer essentially the limiting profile, the limiting regularity into the solution u. Okay. Okay, so this is the idea, Caffarelli. So I would like to do the same idea, develop more or less the same idea for my transmission problem. All right. The problem now is that this is not a single equation. This is an interface, and we have U1 and U2. So let's first set up the geometry. So say we're looking at regularity near gamma. So I'm going to assume that, in the ball B1 here, omega 1 is above, omega 2 is below, and gamma is the graph of a function psi, which is a C1 alpha function. So if I zoom out this is what I have. I have gamma here, I have U1 above, U1 below, the normal points upwards, right? And my gamma, this is the graph of a C1 alpha function. So what is the theorem I need to prove to get the regularity? Suppose that 0 is in gamma. You can always translate the whole picture. And suppose you have a solution to your transmission problem and your G is held at the origin. Then we can do what we want to do. We can find linear polynomials P and Q such that the P, U1 detaches from P in a C1 alpha fashion in the upper part, right? And U2 detaches from Q in a C1 alpha fashion in the lower part, right? Because U1 lives above gamma, so you need a polynomial for U1 and another polynomial for U2. Okay, and then A here is like the gradient of U1, B is the values of U1 and U2 on gamma, and then C is the gradient of U2, and then D is the C1 alpha semi-norm, right, of the gradients. All of those are controlled by the C1 alpha norm of gamma and the C0 alpha norm of G. So this is exactly what we need, that U detaches from a linear polynomial in a C1 alpha fashion from each side, right? So U1 is above here and U2 is below there, so you need a polynomial for U1 and another polynomial for U2. You cannot have a unique polynomial for both because otherwise you will be C1 alpha across gamma, and we saw in the examples that there are always corners. And then, once you have the regularity on gamma, this is the regularity on 0, right, on gamma, then you know from interior estimates that you smooth inside, and you can patch the estimates. And as I said, there is the limited regularity of gamma and G. If we're working with harmonic functions here, and you want to flatten gamma is a curved domain, and you want to flatten gamma in a non-divergence form, you need gamma to be C2 alpha, because you have to take two derivatives of the domain, essentially. But here, just gamma is C1 alpha. And also, there is no way of coupling this U1 and U2, so it's not like I can do everything for U1 and then by some reflection, try to do something for U2, because one solution depends on the other through the interface. Now, what is the idea? The idea, as I said, is to develop the geometric argument of zooming in, right? So the idea is to trap the gamma between two planes and approximate U by solutions to problems with flat interfaces. So this is the parallel of the harmonic function before, right? Here I have my solution U, and I approximate the solution U by good solutions. So solutions to a harmonic, to the Laplace equation, right? Here I say, well, I have gamma, and gamma is curved domain. Well, I'm gonna trap gamma between two flat interfaces. And I'm gonna solve the problem in the flat interfaces and try to see whether those solutions of the flat interfaces are close to the solution to the curved interface. Now, the flat interfaces should give me very nice solutions, smooth solutions, so that then I rescale, right? When I rescale this picture, the blue line becomes flatter and flatter and flatter. And I can put these orange planes closer and closer and closer and closer. So like in the limit at the point, I can transfer the regularity from the flat problems into the curved problem. Okay, so for that, we need to understand first the flat problems, because if the flat problems don't give us good solutions, then we cannot do anything. So what would be a flat interface transmission problem? So a harmonic function in the ball B2, except at xn equals 0. And then the difference of the normal derivatives on xn equals 0 is G, right? So here is a flat interface. Of course, 0 on the boundary of B2. So in this situation, the problem can be actually decoupled. So I can solve above the ball, the half ball in the lower half ball, and then patch them together. So how you do it? Say you solve the Neumann problem Laplacian of v1 equals 0 in the upper part with interior normal derivative g over 2 on xn equals 0. Okay, and then v1 0 on the boundary of v2 plus. So the problem has a unique solution. v1 by classical regularity, v1 is c1 alpha in the interior up to the boundary, right? G here is Helder alpha. So if the derivative is Helder alpha, v has to be c1 alpha all the way up to xn equals 0. So I have v1, now I reflect v1 towards v2 minus. So I consider the reflection, the even reflection. And now obviously v2 is harmonic because v1 was harmonic. It coincides with v1 on xn equals 0, to 0 here. And it's also c1 alpha below because it's just a reflection of the v1. And if I take the derivative with respect to xn of v2, the minus pops out here. So you get minus the derivative of v1 at xn equals 0, which is g over 2. So you get minus g over 2. All right? So now my v, which is v1 above and v1 below, is the solution to the transmission problem because it's harmonic above and below xn equals 0, and the difference of the normal derivatives, this minus this, is exactly g. Okay, so here you can decouple the problem using a simple reflection, solve it. Okay, so now what else do we see? Is the solution good? Yes, because the v1 and the v2 are c1 alpha from each side up to the interface. Okay, yeah, if g is more regular, then v will be even more regular all the way up to the interface. Okay, so solutions to the flat problems are nice solutions. So now I gotta show that if I trap my domain into two planes that are very, very close to the domain, then I have the solution to the flat problem is close to the solution of my curve problem. Okay, let's see. There is a question here. What is the boundary condition on the rest of the boundary? Okay, yes. So here the Laplacian is 0 in v2. So let's look at the normal. The Laplacian of v1 is 0 in v2 plus, right? Then normal derivative is g over 2 on xn equals 0. And in the upper part, I didn't write it here, I put v1 equals to 0. Okay, so if you reflect down, right, the boundary condition above will still be 0 below. So this v, right, on the whole boundary will be 0. Okay, as I said, I can consider something else, right? So if I solve for 0, then I'm fine because I say you want to solve for any phi on the boundary. Well, you just take that phi and you do the harmonic extension and you add it to this one, right? Because this transmission condition doesn't see smooth functions, right? If you have a smooth function across xn equals 0, this difference of the derivatives is 0, right? So if you want to put another boundary condition, you just take the harmonic extension of that boundary condition and add it to this solution that has 0. Okay, because again, as I said, smooth functions have this difference of normal derivatives equals to 0. Okay, so as I said, here is the stability result. The stability is this idea that I said before that if my domain is almost flat, then the flat solution should be close to the curved solution. So say that gamma is theta epsilon flat, so it's in a strip of width 2 theta epsilon, and epsilon horizontal here means that it doesn't wiggle too much inside the strip. So essentially means that the normal derivative, the normal to gamma is very, very close to the vertical, right? So there is no a lot of wiggling inside. So there is no a lot of mass inside the strip. So kind of like this picture, right? This picture here. So this is in a strip, and then the normal derivative, the normal vector here is almost vertical. Okay, is detaches from the vertical by less than epsilon. Now we have the solution to the transmission problem, right? Laplacian of u, a singular measure on gamma, and say now that g is close to 1. Because remember, if g is 0, then this is a harmonic function. Laplacian of u is 0, so nothing to prove. So the significant, remember the beta, the alpha and the beta, the significant case for the transmission problem is G non-zero, say 1. So if G is close to 1, then what should happen? The solution to the flat problem with G equals 1, so I'm looking at the plane minus theta epsilon, and the gamma is a little bit above. With the same boundary values U, that should be close, and it is close to V. I'm sorry, V is close to U, right? And these are all the parameters we need in terms of the regularity of U, the closeness of gamma to the planes, and so on. And the delta here, how close is G to 1, okay? So if the plane is from below and everything is very small, the gamma is very close to the plane and G is very close to 1, the flat problem, the flat solution is close to my solution, to my curve solution, all right? So this is like saying the harmonic extension of the solution in the case of an elliptic equation is close to the solution. And if you put the flat interface above, then you can also do the same. You're just putting here below the interface. Okay, and this is the key to obtaining the regularity. That first approximation. Okay, so what is the idea for the stability result? Say you want to show that U is close to V in less than some constants here, very small. So I want to show, for example, that V is less than U plus that very small constant. Then by a similar argument, you prove that U is less than V plus the constants, and you are done. So let's say you want to prove this. I want to use the maximum principle. So for the maximum principle, I have to check the Laplacian of U and the Laplacian of V and see whether they are one bigger than the other, right? So, but here the problem is the Laplacians are disjoint. So the Laplacian of U lives on gamma, and the Laplacian of V lives on this flat interface minus theta epsilon. So when the Laplacian of U has some mass, the Laplacian of V is 0. And when the Laplacian of V has some mass, the Laplacian of U is 0. So there is a problem that the Laplacians cannot be readily compared, right? So how do you do that? Well, you try to increase the support of these Laplacians, right? And to do that, we do the averages. So we look at U and we do the average in a ball of radius epsilon. And we look at V and we do the average of V in a ball of radius m epsilon, a little bit bigger. Now what happens? So say you have this ball B epsilon, right? And this ball B epsilon does not touch gamma, right? So outside gamma, U is harmonic, right? So by the mean value property, the average is exactly U. So the average being exactly U means the Laplacian of the average is the Laplacian of U is 0, all right? Now when the ball intersects gamma, right, you are integrating here, the epsilon intersects gamma, well, it's going to be the Laplacian of U epsilon. You can think that you can put the Laplacian inside. The Laplacian of U on gamma will be G, all right? So what is happening now? For all x, epsilon away from gamma, the Laplacian of U epsilon is 0. But for all x, epsilon close to gamma, in a band of width epsilon from gamma, the Laplacian of U epsilon is some positive quantity, right? So what happened? The Laplacian of U was concentrated on gamma. Now I increased its support, right? The Laplacian of the averages has support around gamma. Now for V, I do the same, but with larger balls. So remember, the V, the Laplacian of V is supported below the Laplacian of U. But then if I increase, I use this m epsilon to increase the support of the Laplacian of V, I will be engulfing the support of the Laplacian of U, which is shorter. This is why these balls are bigger. Okay, so, and this is because gamma is very close to the flat plane. So the support of the Laplacian of U epsilon is engulfed by the support of the Laplacian of V m epsilon. And now, since one support is contained in the other, I can compare them. And I can prove that the Laplacian u epsilon is less than the Laplacian of v, m epsilon, the average. And so what is the Laplacian of u epsilon? Is this, whenever you pick up some mass, this is what it is. Now I write down using the parametrization, because gamma is a C1 alpha interface, so this is the differential of area, and I evaluated G on the interface. And now I increase, G is not negative, right, it's close to 1. So I increase this domain in the following way. So this is gamma in V epsilon. So I'm going to increase by Bm epsilon, right? And I'm going to look at the y primes, not the only ones that fall, that such that psi of y prime is on gamma, but all the y primes that are also below on that plane minus theta epsilon. That's a bigger domain. You have to do a careful geometric argument to see that this set is containing this. But anyway, you can do it. And after you do that, G is close to 1 by less than delta. So this G is less than 1 plus delta. And you multiply by m to the n and divide by m to the n. And then you have the measure of the ball, m epsilon. And you keep this. And this is some constant, 1 plus theta. Right? So if the V, right, is my solution to my flat problem with a constant, well, 1 plus eta, then the Laplacian is exactly this, right? The Laplacian of the average is this. So the Laplacians are ordered. And then U and V are the same on the boundary of V1. That's how you construct this V. And they're both Hölder continuous. So if you get a little bit inside, by epsilon from the boundary, by epsilon, the difference, U minus V will be of the order epsilon to the gamma. But also the averages will be of the order of epsilon to the gamma. You can check. So what happened with the averages? Their Laplacians are ordered in the interior, and on the boundary, they are also ordered, right? Because V is less than U epsilon plus constant epsilon to the gamma, and the Laplacian of that is the Laplacian of U epsilon, right? So if you have two functions whose Laplacians are ordered, and they are ordered also on the boundary, they are also ordered in the interior. So you apply the maximum principle, and you say that this inequality propagates all the way to the interior. All right. So the average of V is less than the average of U plus a little bit. So this is what we saw. And then for V minus U, what you do, you add and subtract the average of V, and you add and subtract the average of U. Now you know the differences of the average is good, is close to 0. And then here V is Hölder continuous. So this should be of the order m epsilon to the gamma. And U is also Hölder continuous, so this should be of the order epsilon to the gamma. And you know everything is small by epsilon to the gamma. So you prove that V minus U is very small. Okay, so that's the idea of using the mean value property to increase the averages, to increase the supports of the Laplacian of U and the Laplacian of V, okay, which live only on n-1 manifolds, n-1 dimensional manifolds. Okay, and how you continue with this? Now the idea is the same. You zoom, right? Rescale and repeat, rescale and repeat, rescale and repeat. So this is the idea of zooming in. Right? So you have the two planes, you have the solutions V that are close to U, so then the corresponding Taylor polynomials will approximate U at some scale. Then after scaling and iterating, you have planes that are closer and closer and closer and closer and closer. The interface becomes flatter and flatter and flatter, and in the end, the solution U is C1. Okay. Okay, that's it. So future directions, for example, if you want to do divergence form equations instead of just harmonic functions, using this idea of the mean value property. There are some mean value properties for these sort of equations proved by Blank and Howe in 2015. So that would be an idea to explore. The mean value sets, the set where you have to do the averages. For the Laplacians are balls, but for these equations, you know, they're more complicated sets. So, but that would be an idea to explore. With Maria, we are doing the Fourier linear case also instead of having two harmonic functions. And then you can do also local and non-local, maybe not with these ideas, but other ideas are parabolic problems. So there is a lot of things that are still very open in terms of transmission problems. Yeah, so that's it. Thank you very much.